FILA-SoS, which we call the Flexible Intelligent Learning Architecture for System of Systems, it uses the wave process for addressing the four most challenging aspects of systems architecting. The first one being dealing with the uncertainty and variability of the capabilities and availability of potential component systems. The second highlight is basically provides the evolution of system needs, resources, and environment over time. It also accounts for differing approaches and motivations of the autonomous component systems managers. And then finally, it optimizes system characteristics in an uncertain and dynamic environment with big fixed budgets and resources. FILA-SoS does so using straightforward system definition methodology, an efficient analysis of framework that supports the exploration and understanding of the key trade-offs and the requirements by a wide range of system stakeholders and decision makers. The wave model is the fundamental building block of the FILA-SoS, and it has been proposed before, and we just kind of implemented that for a system application. It starts with the conduct SOS analysis, develop an SOS architecture, plan for SOS update, and implement the SOS. That becomes one wave. And as we could see in the slides, these waves repeat one after the other as the architecture SOS system matures along the way. The way that the FILA-SoS has been built, it has basically eight modules. And then through these 8 modules, we were able to represent the wave process. And then if you want to look at it, how they're all related together, the wave process requires the initialization of SOS. And that's basically understand the SOS objectives and operational concepts, gathering information on the core systems to support desired capabilities. In FILA-SoS, what we do, we provide the inputs values required to run the FILA-SoS, which include a number of negotiation cycles, meta-architectures, generation, model selection type, and individual negotiating model types. Then the second phase of the wave process was conduct SOS analysis. Is basically the wave process indicates the establishment of an initial SOS baseline architecture for SOS engineering based and associated requirements-based performance measures and relevant planning elements. That's what has been conducted in here in the wave model. In the terms of FILA-SoS, this converts itself to execution of meta-architecture generation model, and it has to go back and selects an initial baseline architecture using the given input data for the domain. The next phase of the wave process was develop and evolve SOS, and then that's basically the identification of necessary changes in contributing systems in terms of interfaces and functionality in order to implement the SOS architecture. And then the FILA-SoS considered this step through connectivity request to individual systems and the start of the negotiation process between the SOS and individual systems. The next phase of the wave process is planned SOS update. And then this is basically planning for the next cycle of SOS upgrade cycle, and that provides the changes in the external environment, SOS priorities and operations and backlogs. And then in the case of the FILA-SoS, this transfers itself to determination of which system to include based on the negotiation outcomes and form a new SOS architecture. Then we go ahead and implement the architecture with the wave model. And then that's basically in the FILA-SoS, this is considered as the evaluation of negotiated architecture quality, and decide to renegotiate or move on the next acquisition wave. That's basically the negotiation cycle starts. The way that the FILA-SoS creates our initial architecture at a very high level, there's a selection of system and interfaces. It does not provide enough behavior that we are looking for. In order, before we move into the next step, we have a capability to run to see how the architecture will behave, and this is run through the SOS behavior object process model, which is based on the OPMs and also the color patterns to see whether various scenarios that we picked up can be achievable in the SOS that has been negotiated. And that's how it's related to between the wave process and FILA-SoS. If you look at it, the capabilities of the FILA-SoS is basically provides integrated model for modeling and simulating SOS system with evaluation of multiple ways, and this is something new. And then all the 8 models that we have, it can run effectively independently, and they can also run in conjunction with other. So in a way, FILA-SoS has a capability to run models independently, as in terms of the 8 independent models that created the integrated version of the FILA. We have different model types representing the behavior of and also various individual system behavior. So we can represent the SOS behavior. Also, we can represent the individual systems that are contributing to SOS behavior. And then we can study the simulation dynamics between the SOS and the individual systems. FILA-SoS will provide a what-if capability and model modularity. For example, the variables that we have incorporated in the FILA-SoS as funding, capability priority can be changed as the acquisition process progresses through the wave cycles. We have the capability to see the simulation of any architecture through color patterns. We can easily have a capability to be able to simulate the rules of engagement and behavior setting, and then in that way we can consider all systems non-cooperative, all systems are semi-cooperative, all systems are cooperative, or various combination of those, and see what the action will be, what the negotiated architecture will be. Now, we would like to ask what the value that FILA-SoS provides. It basically is an decision aid for SOS manager in making future decisions. It provides the understanding the emergent behavior of the system acquisition environment and its impact on the architecture quality. It can go ahead and study the dynamic behavior of different types of systems, as we have indicated as cooperative, semi-cooperative, and non-cooperative. It also has the capability to provide as a value to identification and interdependencies among SOS elements and the acquisition process. FILA-SoS is a general model which has certain assumptions, of course, but it can be applied different areas, such as variety of complex system models, such as logistics, cyber-physical systems. It provides a test bed for decision makers to evaluate operational guidelines and principles for managing various acquisition environment scenarios. And then it is applicable to system of systems that evolve as it has multiple base simulation capability. What we are trying to do in the future capabilities, the version FILA-SoS version 2.0, we are trying to, as a future capability, it will be possible to integrate risk models into environmental scenarios. extending the model to include multiple interface alternatives among systems. Once we have negotiated the architecture, or if you want to determine what type of scenarios and actual behavior will occur in the architecture itself, we have to use the object process methodology and color pattern nets, and that's basically creates an executable architecture model. And the details of this model will be given to you by Dr. Renzhong Wang, and he works for the Sprint Research at this time. He was a postdoc in this project earlier.
In this presentation, I will be focusing on the executable model developed by the FILA-SoS. The operations of the SOS is a dynamic process with participating systems interacting with each other and exchange various kinds of resources between each other. These resources can be abstract information of physical objects. Some performance measurements are the result and the reflection of such interaction or behavior in general. For example, during the operation of an intelligent surveillance and reconnaissance system of systems, there are some things that does not stay still and remain constant. If we want to evaluate the coverage area and the latency of an ISR, we will see that the reconnaissance systems need to have a break after operating for the maximum allowed period. With systems going on and off duty, the total coverage area by these systems might fluctuate. Furthermore, the observations may not arrive at fixed intervals, and the capacity of the data processing systems may be overloaded or underloaded during the operation. Therefore, the latency might also vary. Such variations resulting from the interactions of the constituent systems are rather difficult to estimate statically. That is the motivation of introducing the executable modeling approach into our FILA-SoS solution. Particularly, this modeling approach can model the interactions between components of the system or subsystems within SOS. It can capture the dynamic aspects of the SOS and simulate the behavior of the SOS. It can assess various behavior-related performance and assess different constitutions or configurations of the SOS. Here we use an example to explain this executable modeling approach. This slide presents an object-oriented, object process methodology model for the ISR system of systems. The participating systems are classified into 4 types and are represented as objects in this OPM model. They are reconnaissance systems, communication systems, exploitation centers, and command and control systems. Each of these systems has some behavior or operations. We call it a process in this OPM model. Each of a behavior has some effects or can yield certain results. In this example, we can a process can change the state of an object. Particularly, there is a data object in this model. It is an abstraction of all kinds of information being processed by this system. A particular form of information associated with a processing state of the SOS during operation is modeled as the state of the data object. Here we see that initially raw observations then being transmitted, analyzed by various systems, and eventually become action plan that guides the further operation of this ISR. It is called an object process methodology because we can see both objects and the process in one model. So on one hand, objects own the process. On the other hand, the execution of a process requires the support of one or more objects. These systems, its objects in this model is described by a set of attributes that further defines the system. We use these attributes to describe the parameters that are used in the simulation as well as performance assessments. The OPM model is intuitive and easy to understand. However, it does not support simulation, with it required for assessing the behavior related performance attributes. However, it is easy to map the OPM into another executable modeling language called colored Petri net. Colored Petri net, we call it CPN in short, has a graphical appearance. As we can see, it is a biparty graph contains of places represented by oval shapes and the transitions represented by rectangles and the arcs connecting them. Places carry markers called a token, but we don't see it in this graph, but we will see it in the simulation later. Those tokens mark the state of a system. Transitions describe the action of a system. The arcs tells how actions modify the state of and when they occur. And when certain conditions hold, a transition will be fired, causing a change in the placement of tokens, and thus the change of state of the system. Under such graphical interface, CPN has rigorous mathematical definitions that support simulation as well as supporting various kinds of quantitative analysis. And now I think I would like to demonstrate the simulation of this CPN. Here is the colored Petri net model for this ISR system. Those notations are purely execution semantics. In this place, we see the tokens. They represent the kind of reconnaissance systems that are deployed in this system. And we also have some other tokens that give the initial setting of this system. If we run this simulation, then we will see these tokens change these places. And I'm running this simulation in one step, so you will see its final result. Okay, now the simulation is finished. We can see there are tokens being added to some of the places in this system, and these tokens carries the information that we need for computing performance-related measurements. measurements. For example, this slide shows the simulation results. From the simulation, we know that based on a certain system setting, the ISR system used 20.07 minutes in average to finish all stages of information processing, from raw observations until to the final action plan. And in average, 2.08 minutes are spent in waiting. Minimizing this waiting time can minimize latency. In terms of coverage area, we found it fluctuates along with time, as shown in these figures below. And we can compute the average minimum and maximum coverage area based on such information. In summary, CPN models and their simulations contain detailed quantitative information about the performance of a system, such as throughput, processing time, query length, and resource utilization. This quantitative information can be extracted to support the investigation and discovery of structure and the dynamic system properties. OPM, on the other hand, provides an intuitive system model, much easier for a human to comprehend. And the OPM model can be mapped to CPN, so we can have a full executable model, easy to understand and also executable, and support performance